In this video, we'll be doing the type of relative motion problems called rain on windshield problems, or I decided to call them rainfall on window problems. So I've got two examples for you. Example problem 1. A car travels due east with a speed of 50 kilometers per hour. Raindrops are falling at a constant speed vertically with respect to the earth. The traces of the rain on the side windows of the car make an angle of 60 degrees with the vertical. Find the velocity of the rain with respect to A, the car, and B, the earth. So let's start by visualizing this. So we've got a car. It's going at 50 kilometers per hour. And we know that the raindrops are falling at a constant speed vertically with respect to the earth. So in order to visualize that better, let's have this dude. So this dude is stationary, and the raindrops are falling vertically. And they're falling vertically onto the car, but since the car is moving, it's not going to look vertical to the car. It's going to make this 60-degree angle. So zooming in on what's actually going to happen on this windshield. So the rain is falling, and that's the vertical. And the rain will make an angle something like that. And that angle with the vertical is 60 degrees. So what we want to find is what is the length of this vector. That would be the velocity of the rain with respect to the car. And we also want to figure out with what velocity was the rain originally falling with. So, like I said, that's the velocity of the rain with respect to the car. And then that blue arrow that I just put in, that's the velocity of the rain with respect to the earth. And then this green line, well, it's a little bit confusing to think about. So let's go back to this one for a second. So this represents the velocity of the rain with respect to the earth. Okay, now I want you to imagine that you're in this car, and what you'll see is you'll see the rain fall sideways like this. So this is a vector, and this vector can be broken down into an x component, which is represented by the green arrow, and a y component, which is represented by the blue arrow. So the blue arrow is the velocity of the rain with respect to the earth, but it's also the velocity of the rain with respect to the car in the y direction. And then this, the velocity of the rain with respect to the car in the x direction, is just equal to the speed that the car is traveling with. So remember, if you're just traveling at 50 kilometers per hour, then everything that you pass is going to look like it's moving backwards at 50 kilometers per hour. So that's essentially what's happening with the x component of the rain here. So now we have enough information because we've got this angle and this side of the triangle to figure out the other two sides of the triangle. So let's do part A first. We want to find the velocity of the rain with respect to the car. So that would be VRC. So if you look at the triangle, the sine of 60 degrees is going to be opposite, which is 50, over the hypotenuse, which is VRC. Then I'm going to multiply both sides by VRC. And then I'll divide both sides by the sine of 60 degrees. And you get 57.74 kilometers per hour. So this is our answer to part A. And then part B says we want to find the velocity of the rain with respect to the earth. So that's going to be VRE, this side of the triangle. So you could use the Pythagorean theorem. I like the trigonometric function, so I am going to use the tangent here. So the tangent of 60 degrees is opposite over adjacent. So that would be 50 over VRE. Multiply both sides by VRE. then divide both sides by the tangent of 60 degrees, and you get 28.87 kilometers per hour. So that's our answer to part B. And I just want to point out that our answer to part A makes a lot of sense because it's going to look like the rain is moving faster from the point of view of the car because the car is moving forward. All right, example problem 2. Raindrops are falling vertically downwards at 7.1 meters per second. A man runs horizontally in the rain at 4 meters per second. We want to find the speed of the rain relative to the man and the direction of the rain relative to the man. So we're going to visualize this one as well. So we've got the rain just falling vertically, and it is falling at 7.1 meters per second. And it's falling on this man who is running at 4 meters per second. So instead of a window here, we just have what the guy here sees. So let's zoom in on that perspective a little bit. So the rain is falling vertically, but the guy will see it falling at some angle to that vertical motion. So the guy will actually see it, he'll see it fall vertically at 7.1 meters per second. So the velocity of the rain relative to the earth is the same as the velocity of the rain relative to the man in the y direction. So here's how the man will see the rain. And he'll see it at, this will be the velocity of the rain relative to the man, and he'll see it at some angle. And then we have to have an x component of the rain relative to the man. And again, that'll just be this 4, because when you run forward, it seems like the things you're moving past are actually moving at that same speed backward. So the x component of the rain will look like it's going at 4 meters per second in the opposite direction. So we've got 2 sides of the triangle, so we can find out the length of this side pretty easily if you use the Pythagorean theorem. So part A will just be the velocity of the rain with respect to the man is equal to 4 squared plus 7.1 squared, all in a square root sign, and that ends up being 8.15 meters per second. And that makes sense like the previous problem did, because since the guy is moving forward, he's going to see the rain going at a faster speed than it's actually falling. And then for part B, we want to find the direction. So we want to find this angle here. So we can use the tangent function because it's opposite over adjacent. So it'll be the tangent of 4 over 7.1. Then you can just take the inverse tangent of both sides to get the angle. And it'll be 29.4 degrees. And technically that would be relative to the vertical. So the direction words you can write there, you can just say relative to the vertical and abbreviate it like that. So hopefully you have a better idea of how to solve rain falling problems now using relative velocity.